Great, it's look like I am live now. So, without any further delay, let's just start. Okay, so I'm here to understand the key concepts in RL. RL. Key concepts and RL. Okay, this is FNI documentation. Okay, part 1, part 2, and total policy optimization. Okay, great, great. Yeah. Core maths. Try करते समझ पाते हैं if you can understand. It's a very good definition. Industrial RL is a study of agents and how they learn by trial and error. Agents and how they learn by trial and error. अवनी भाई different moment allow different kind of actions. ठीक है? The set of right actions in the given moment. अच्छा ओके ये पॉलिसी आपका पैराफिन पॉलिसी kind of it is kind of home kind of home and deciding which which action to take और ये दोनों हो सकता है डोमेस्टिक भी हो सकता है डोमेस्टिक भी हो सकता है तो हो सकता है जैसे और stochastic also to parameterize policies that is policies whose output are computable functions that are going to deployment. At Russian businesses with pressure coordinator essentials technology.
ଆସିନି ଦେଖ କିଏ ସବମିଟ କରିବ କିଏ କାହିଁ କିଏ ଏଠି ଦେଖଉଛି ନା ତ ହଁ ଖୁଲେ হ্যাঁ বেকাରିଆ କଥା କହୁଛ ଖାଲି କିଏ ଏଠି 22 एमई 6000 6004 ଆଜ୍ଞା କିଏ ସବମିଟ କରୁଛି ବେକାରିଆ କଥା ଅନର ଖବର କରିନି ଦେନେ କେଡି ଖବର କରିନି ଆରେ ବେକାର କଥା କହୁଛ କେଡି ଖବର ମତେ ବୁଝେଇ ଟିକେ ଇଏ করে ଇଏଟା କର ଆରେ ମାଇକ୍ରୋସଫ୍ଟ ମୋର ଇଏ କର তোমাকে লজ্জা করছো আসলে কাজে টাউটরি মারুছো কথা আসো এমএস করো हेलो केडी देखो केडी टाइम તમે ये करो તમે शेयर कर दे स्क्रीन शेयर करो टाइम देखा देखा भी हां देखा ମୁଁ ହଉଛି এটা ମୁଁ ଭୁଲ ଦେଖାଉଛି ନା କଣ ହଉ ତୁମର शेयरिंग ଟା କାଟ କେମିତି ଦେଖିବି ଏଟା ଆରେ ମୁଁ କରିନି ଏଟା
advantage function
ମୁଁ ଏଟା କରିବି କଣ ଆଜ୍ଞା ମୁଁ ଜାଣିନି ଏଟା ଡିଲିଟ କେମିତି କରିବ তোমার দেখো দেখি দেখো কি এটা সেই দেখো ଆଉ ଦେଖଉଛି ସେଟା ସେଟା ଦେଖଉଛି
please share it
ହଁ ଯାହା ବଢିଆ ବେକାର ମୁଁ ଲେଖା ଷ୍ଟାର୍ଟ କରିଛି। ହଁ ବେକାରିଆ ଜିନିଷ। ଆରେ ସେଗୁଡାକୁ ଇଏ କରିକି ଭଲସେ ଲେଖିତେ হবে। ଆଜ୍ଞା ତାକୁ ଇଏ କରିଦେବ ଭଲସେ ଇଏ କରିକି ମାନେ ଟିକେ ଲିପି କରିକି ଲେଖିତେ ହେବ ନହେଲେ ରସ ଖାଅ ନା କଣ? ମୁଁ ତ ତାକୁ ଟିକେ ପଢି ପୁଡାକି ଲେଖୁଛି ମାନେ ଏଇନୁ ଟିକେ ପଢୁଛି ସେଇନୁ ଟିକେ ପଢୁଛି ଏରକ କରିକି ହୁଁ। ଆଉ ତମେ କଣ କର ତମେ ପଢୁନ ନା କଣ ତମେ କରିବ ନା କଣ ସେମିତି? ଆଉ ସେମିତି କର ଆଜ୍ଞା ଆରେ ମାନେ ଟିକେ ଭଲସେ ଇଏ କର ମାନେ ଟିକେ ଭଲସେ ଜାଣିପାରିବ ଆଉ ଭଲସେ ଲେଖିଦବ ଆଉ। ହୁଁ ମୋର ଛାଡିକି ଭାଇ ବେଶୀ ଭଲ ଦେଇଛି। ମୋର ଛାଡିକି ଭାଇ ବଢିଆ ଦେଇଛି। ଆରେ ମୁଁ ମିଶିକି ଲେଖୁଛି ତ ମତେ କିଛି ଧରିପାରିବନି। ହଁ ମତେ ଧରିପାରିବେନି ଅବସ୍ଥା ଆ ସେମିତି ତ ସମସ୍ତେ କରୁଛନ୍ତି କିଏ ନ କରୁଛି। ଆଉ କଣ କରିବା ଆଜ୍ଞା ହଁ ଆଉ ସିଏ ବି ଭଲସେ ସେ ମ୍ୟାମ୍ ବି ଭଲସେ ଜାଣନ୍ତି ବୁଝିଗଲ ନା। ଯେଉଁମାନେ ଚୋରି କରିବେ ଠିକ ନା ନୁହେଁ? ଖାଲି ଗାଲି କଥା କଣ ହେଲା? ଆରେ ସେତିକି ୱାର୍ଡ ଲେଖନି ଆଉ ଟିକେ ଅଧିକା ଲେଖିଦିଅ ସେ ସବୁ ବେକାରିଆ କଥା ତାର ଲେଖନି। ସେ ସବୁ କିଏ ଗଣୁଛି ନା କଣ ୱାର୍ଡ? ଆଜ୍ଞା କିନ୍ତୁ ଆଉ ଟିକେ ଅଧିକା ଲେଖିଦିଅ। ହୁଁ ଆରେ ଆଜ୍ଞା ଆରେ ବେକାରିଆ keyboard. And underline. Yeah. Copy करना बेहतर है. अरे ना बेहतर है ढाई चार दिन का 40 डायरेक्ट कॉपी करिए ना अब आने की गूगल डॉक्स पर कैसे तो पूरा पढ़ा ब्लैक कलर देगा. ଆଜ୍ଞା मैं बेहतर है. हाँ डायरेक्ट कॉपी मध्ये बेहतर है. शिक्षक बेहतर है जिसको पता कोई ना होता है. बेहतर है. त्यांच्या लास्ट लक्षासाठी होण्यासाठी मला ट्राय करूया जे ये करूया मला लॉस काम बेहतर है. हाँ धन्यवाद. धन्यवाद. What is this for? हाँ एक जेल माने की कुत्ते को बेहतर है लैंग्वेज एक्सेप्ट इंडियन लैंग्वेज. ଆମର ୟୁଜ୍ କରୁଛେ କେନା ଆମର ପ୍ରଥମରୁ ଇଏ ହେଇଛି ନା ସବୁ ଜିନିଷ ଆଉ ତାପରେ ନେତାମାନେ ବି ବେକାରିଆ ଗୋଟା ନହେଲେ ଆମ ଲାଙ୍ଗୁଏଜ ଓଡ଼ିଆ ଜାଣେ ମୁଁ ତ ସେଇ କଥା କହୁଛି ଆମ ଲାଙ୍ଗୁଏଜ ଓଡ଼ିଆ ତ ବେକାର. সত্য কথা মোর তোমার বেস্ট কথা ভাবিনি করবো মজা ছাড়ি ইয়ার পেছনে ছাড়ি যায় 3 পেজ अरे देवड़ा ये गुला काट देंगे अरे तुम्हें ये कर दिए ये उड़ा माने मेन ये उड़ा को ताको ये पॉइंट देके एक ग्रांड देके देखिए बड़ा तो ग्रांड दे दे जब माने ये पॉइंट होगा ऊपर टाइजर अरे गार्ड देखना डिस्टिंग इसको या ये लॉस को जरा कौन होगा एक दुई तीन अरे मात्र 3 कौन কথা আর ওটা বড় করতে
After TRPO, Actor, and PPO, let us have a look at DDPG and TD3. These algorithms use a deterministic policy, and as you will see, it is easier to explain them by starting from Q-learning and deep Q-network. So in Q-learning, you have a Q-table, okay, where for each state, you have the value of taking each action. In deep Q-network, you put the state as input, and you have one neuron per action, where the output value of the Q-network tells you the value of being in that state and taking that action, okay? So you can see the deep Q-network as a kind of Q-table, where in fact you can put an infinite number of different states, so you have a Q-table with an infinity of state rows. Okay. And each of these state, when you want to perform an update in your Qtable or in your Q-network, you will apply this update rule, okay, which is the standard Q-learning rule, using here the temporal difference error. Okay. You will select the action by taking the max over the actions in the state. So you look for a given state and you take the max. Okay. And the limitation of deep Q-network that will be overcome in DDPG is that you need one output neuron per action. And if you have continuous action, of course, you cannot have one neuron per action because you have an infinite number of actions. So there are two limitations when you want to move to continuous actions. Two things, in fact, become too hard. One consists in selecting actions by finding the max over the actions for the given state. Okay, that's an optimization problem. You want to find a max in a continuous domain. And the other one is in the update rule. You need to also find the max over the actions of the Q values of the actions in the next state. Okay. To do this, there are three classes of solutions. One consists in having a simplified version of the Q function where it is easy to find a max. This is used, for instance, in NAF, okay, where in fact the Q function is just quadratic, so it's easy to find a max in a quadratic function. Another approach consists in just considering a small set of actions and taking a max over these actions. You can, for instance, pick a large number of random actions, or you can do a little bit better. This is what is done, for instance, in Qt-opt from Kalashnikov et al., where they use functions that are likely to provide good Q functions. And DDPG, what they do is something a little different. In fact, they will train a side estimator to find the best action, and the side estimator is the actor. Okay, the idea is that the actor will provide an estimate for a good action, and you will improve this actor, so it will give you a better and better estimate of the max action. So what's DDPG? In fact, as we have seen before, most of the theory about the policy gradient theorem, etc., is for stochastic policies. So in this paper, David Silver has proposed a deterministic version of the policy gradient theorem, so that the deterministic policy gradient, and DDPG is based on this deterministic version. Besides, it uses a lot of insights coming from Deep Q-network. As you will see, we will reuse the replay buffer shuffling ID and also the idea of target Q-network. And in the original paper about DDPG, they also proposed to use batch norm, but later studies proved that using batch norm has an inclusive impact that depends on the problem. Sometimes it helps, sometimes it does not. So in new versions of DDPG, batch norm is not always included. And to publish their DDPG paper, they did as for DQN, they used a large number of benchmark. Here this was classic control benchmark, sometimes from Pixel, to show that they were able to learn controllers for very different problems. So let me now explain the architecture of DDPG by contrasting it with the architecture of Deep Q-network. In Deep Q-network, as I just said, you have one output neuron per action, and you will find the best action by selecting the one that has the highest Q value. In DDPG, you have continuous action, so you cannot do that. So what they do is the following. You have two separate structures. One is the critic and one is the actor. So to be able to deal with continuous action, what you will do is that as input you take the state and the action, and you have a single output neuron that tells you what is the value of taking that action in that particular state. Okay. So if you want to compare two different actions, you will have to put the state and the action as input twice and then compare the Q values. That's not very convenient. So this is not exactly what we will do. And besides, to determine what is the action you should take, you have this other structure, which is the actor. You give it the state, and it gives you the action. And the idea will be to improve the actor so as to take better and better action, as I just told you. Okay. All the updates in DDPG are based on stochastic gradient descent, using adaptive gradient descent techniques from standard PyTorch and TensorFlow libraries like RMSprop, Adam, Adagrad, etc., etc. Now let's look at how to train these networks. First, we have to look at how to train the critic. The general idea is exactly the same as in DeepQ network, but there is a minor change due to the fact that here we have an actor-critic architecture rather than a Q-table. So this idea is the following. In supervised learning, generally you minimize a loss function, which is a squared difference between some target value and the output of the network that you are trying to train. And okay, so you want to minimize something so that it goes to 0. And in reinforcement learning techniques, the critic will be accurate if the temporal difference error or the reward prediction error goes to 0. So we would like to minimize this temporal difference error. And you have something very similar in DeepQ network, but in DeepQ network here you are taking the max over actions of the Q values at the next time step. In actor critic methods you cannot do this because you cannot find this max. So what you do is that you take the Q value at the next time step, considering the action that your actor will provide. Okay, so this is your temporal difference error, and the idea is to minimize this error. And if you look closely at the structure of this equation and this equation, here the idea is to take this part as target value. Okay? If you take this part as target value, then you get something which is very similar to that. And by making so that the loss converge to 0, then the temporal difference error will converge to 0, and your Q network will get accurate. So to perform this computation, so to get this target value, what you do is that you take a mini batch of n samples where you have the current state, the current action, the reward, and the next state, and a target network. I will explain about this target network just after that. And you compute these values from those samples. Okay. Finally, once you have this target value, then you can update your critic parameters by minimizing the loss function corresponding to the squared distance between your target value and the output of your network. So that's very similar to DeepQ network, but here you are using a slightly different equation for computing the target value. So let me now explain the story about the target network. In the tabular case, when you are doing Q-learning, each Q value is updated separately, so you have no problem. But in the continuous state and action setting, if you update some value here, it may have some impact closely. So what you will do is that to take into account the interdependencies between the different updates due to the fact that you are using function approximation, you will minimize the squared temporal difference loss function over many batches. Okay. And here I represent the fact that you have a target which is a red ball, you have the current approximation, and by minimizing the squared temporal difference loss function, you will try to minimize the residuals, so you will move your green function toward the red balls. Okay. But the point is that in Q-learning in general and in DeepQ network, and that's also true in DDPG, your target value itself depends on the output of your Q function. So if you move the function to go towards this red ball, in fact, at the same time, the red ball will move away. So what may happen is that by moving this green curve here, you move the red ball, but by moving the red ball, you are moving away, so you need to move the red curve again, and this may go towards infinity. So this is not truly supervised learning because the red balls are moving, and this is unstable. So the key idea in DeepQ network is to transform this problem into a more stable problem by considering periods of supervised learning where the red balls don't move, you converge to the red balls, and from time to time you move the red balls and you converge again to them. Okay. So to do this, you will compute your target value, so your loss function, using a separate target critic which has different parameters phi prime. Okay. And instead of computing your target value with the Q network, you compute it with the target Q network, which is not updated as often as the Q network. So in DQN, you just update this Q network each k iterations For instance, you will play 5,000 of episodes of supervised learning, and from time to time you will update FreePrime to be Phi again, so that your target network matches the current Q network from time to time. In DDPG, we take a slightly different approach. We rather update Phi prime by tracking Phi with a small gain tau using this equation. Okay? And this is slightly more efficient in the context with continuous state and actions. So now what about training the actor? If you remember well, in the case of the policy gradient theorem, when we are using stochastic policies, we compute a gradient as an expectation of over the current state and actions of a log probability of taking the action given the state. But here we have a deterministic policy, so we don't have a probability to take an action in a state. So from the work of David Silver, it was shown that in the case of a deterministic policy, the gradient can be expressed this way. Okay, so what's the intuition behind this equation? The idea is as follows. If you take a state and determine the action, what you would like to do is to improve your actor. So you would like to know if by changing a little the action, the Q value of taking that action in this state will slightly increase or decrease, okay? And you would like to perform the changes that towards actions that will increase the Q values. So in fact, what you want is to estimate the gradient of these Q values with respect to the action. And if you make so that the actions of the Q value were of considered on this lesson, and it has probably been explained before, and I manage the replay buffer, that I like finding the OP about algorithm. The general idea between TD3 that I want to retain is that all descendants of Q-learning algorithms suffer from what is called an overestimation bias. Okay, and I won't explain this, but this has probably been explained before in previous classes. So here you have an example of the average Q values in a problem where those Q values tend to overshoot, okay, before decreasing again. And you can get something which is faster to train and more accurate. And of course, welcome everybody. My name is Olivier Sigaud. I am a professor in computer science at Sorbonne University in Paris.
Olivier Sigaud.
Welcome to these lessons about policy gradient and actor critique methods. In this first video, I will just introduce the general topic and say what I will cover. So let's start with a kind of big picture of reinforcement learning to explain what the other one, but mathematically. A third people, and I also want Welcome to this class about policy search and policy gradient methods in the context of deep reinforcement learning algorithms. There are
Welcome to So we're using update on this. We've seen this before. Or shift the phi.
Okay, 210.
Hi, I am Peter Beal.
अब सुधारता हूँ।